Hello everyone. In this video lecture, we are going to look at how to write a MATLAB code for algebraic method, which is one of the methods to solve a linear programming problem. So I just hope before watching this video, you are already clear with linear programming problem and what does it look like, and a brief algorithm of algebraic method. You should also be familiar with that. But still, I'll just explain you very quickly what exactly is algebraic method, and then we'll go to the MATLAB code part for it. So we are given LPP. So LPP looks like maximize or minimize. Z equals to some cost function is there, C transpose X. So basically it's like C1x1 plus C2x2 plus Cn xn. So we have n variables and C1, C2, Cn are their cost. So this is objective function which we want to get a maximum or minimum value of. And then we have subject to certain constraints. So we have certain set of constraints with us. They may look like a11x1 plus a12x2 plus a1n(xn) less than equals to or greater than equals to or equals to b1, and so on. So we have m constraints into the system, a mn xn equals to bm, and all xi's are non-negative. So that's how the matrix form of a linear programming problem looks like. So what we do basically in algebraic method, the first thing we do is convert the LPP into standard form. So standard form has three conditions. The first condition is right hand side is non-negative. So this is the right hand side, which is b1, b2 up to bn. So first thing is we have to make that non-negative. Second thing is your constraints should be all equations. So these constraints in general can be less than equal to type, greater than equal to type, or already an equation. So if they are not an equation, we have to convert them into an equation. For example, if we have say 2x1 plus 3x less than equals to 4, I have to convert it into an equation by adding a slack variable s1 equals to 4. And similarly, if we have some constraint greater than equals to 3, then we convert it into an equation by subtracting some variable and call it surplus variable equals to 3. So we pretty know that how to convert an inequality into an equation. And the third requirement is the all variables are non-negative. So you have all variables non-negative. So that's the first requirement. So if your LPP is satisfying these three conditions, it is said to be in standard form. And if it is in standard form, we are good to apply the algebraic method. So what we do basically in algebraic method, we first write the coefficient matrix. So this is the coefficient matrix, which are the coefficient vectors of a11, a21, am1. So the first column of coefficient matrix is the column vector of x1. The second column is the coefficient vector of x2. So here it will be a12, a22 and am2. So it's very easy to write the coefficient matrix a1n, a2n and amn, and more columns will be there because this is the original coefficient matrix. But when you will convert your LPP into standard form, so you can see the new variables introduced, slack and surplus. So they will also have their coefficient vectors respectively. So that also needs to be added. So we need to input the coefficient matrix after converting into standard form. And then the right hand side vector is just this one, b1, b2, bm. Because we have already converted that to non-negative, and we also assume we have already made the variables non-negative, and this is going to be the cost vector. So we are going to play with the cost vector in the last, but first thing is we have to look for the basic feasible solution. So how to obtain basic feasible solutions from this? So you have to create a basis matrix of size m cross m, because the number of constraints, the number of equations is m. So basis matrix has to be a square matrix. So therefore we put n minus, so suppose K is the total number of variables, say n is the original variables, and after converting to standard form, K is the total number of variables, then K minus M variables will be substituted equals to 0. Because we are just solving for m variables, the remaining extra variables are substituted equal to 0. And once you substitute that many variables equals to 0, so we get a square matrix which can be solved, because the system after that looks like bx equals to b, which can be solved like x equals to b inverse b, provided this determinant of b is non-zero. B inverse should exist. So that's the meaning of finding a basic feasible solution. So now there are plenty of basic feasible solutions possible. So let me give you the exact number, how many basic feasible solutions we can find. Because when I'm saying the put k minus m variables equals to 0, so you have to choose which variables to be putting equals to 0. Those equal to 0 variables are known as non-basic variables, right? So this gives us a choice, a possible combination. So the total number of combinations is going to be KCM, where K is going to be your total number of variables and M is your number of equations or constraints. So this much is the total number of basic solutions your system will have, and then few of them will be feasible, few of them will be infeasible. So feasible means they satisfy the non-negativity restriction, and infeasible means they do not satisfy the non-negativity restriction. So that's just a very brief overview of algebraic method, and now let's just move to make a program for it in MATLAB. So this is the LPP which we are going to solve. So let me give you the linear programming formulation. Maximize 50x1 plus 120x2 subjected to x1 plus 2x2 less than equals to 100, x1 plus 3x2 less than equals to 120, and x1 plus x2 less than equals to 110, and both of these variables are non-negative. So that's a very simple two variable problem we are given. We are going to test our code on this problem, and so as I just told you that first thing you have to do is to convert this in standard form. So this is very easy to convert in standard form. So maximize 50x1 plus 120x2, and then we have to know that the first condition is all variables should be non-negative, so they are already non-negative, and then the right hand side should be non-negative, it's already non-negative. The only thing we need to do is to convert these inequalities into equations. So that's I'm going to do right now. So plus some first variable, so slack variable, the second constraint changes to plus s2 equals to 120, and the third constraint changes to plus s3 is equal to 110. So this is our standard form, and we know the slack variables default have zero cost, so you also need to reflect that into the objective function. So once you have done this part, so we are all ready to write the MATLAB code for it, but there we need to input the values in the form of vectors. So what vectors we are going to input there? So firstly we'll be inputting the cost vector C, so that will be 50, 120, 0, 0, 0. The right hand side vector will be 100, 120, 110 transpose, because it depends upon the syntax. If you input these as row vector, then you have to write a transpose over here. So B has to be a column vector, as you will see. So you have to write a transpose over here. And the coefficient matrix which I am going to input is going to be this. So first column is the column of x1. So it's 1, 1, 1. The second is 2, 3, 1. The third is the column vector of S1, which is 1, 0, 0. The fourth is going to be the column vector of S2, so which is 0, 1, 0. And the last is 0, 0, 1. So you can see the size of the matrix is 3 by 5. because after converting to standard form you have now 5 variables. So you should have 5 cost, and 3 is the number of equations, so you should have 3 right hand side values. So now the dimension is all correct. We can go towards writing the MATLAB code of algebraic method. Okay, so let's look at how to write step-by-step code for this algebraic method for solving a linear programming problem in MATLAB. So let me first start with just writing this CLC and clear all, just in case. That's a good habit always to start a MATLAB code by writing these two commands, because it clears off all what is present there in the old workspace and your command window if anything is there. So after doing this, we have to go further by creating a section where I have to give the input of my program, of my LPP. So the LPP, in which the coefficient matrix is included, the right hand side vector is included, the cost coefficient vector is included. So all those things I have to input here. And one thing here, so this before writing this input, you convert the LPP in standard form. I have just explained you the meaning of standard form, so that's a requirement before doing this code. Only then you come to this MATLAB part and then you start inputting your data. So the first thing which I'm going to input is the number of variables. So let n be the number of variables. So you can choose any variable of your choice. So here n is the total number of variables I'm pointing at. So after doing it, after converting to standard form, then you count the total number of variables, including the slack and surplus. Then you write this number. So whatever LPP I am having, according to that, I have 5 decision variables. So this is the 5 number of variables. So this is my number of variables. Next, we are inputting m. This is 3, which is the number of constraints I have. So you can see from the LPP that I have 3 constraints in my system. So this is done. And now I'll be inputting the coefficient matrix, right hand side vector, and the cost vector. So let's first input the cost vector. So originally your problem had just 2 variables. So the two original costs were 50 and 120, and the new 3 variables which are added are slack and surplus variable. They are slack variables. So default cost of slack variables we know is 0. So this is my cost vector. And then I'm inputting the right hand side vector, so denoting it by small b. These are the conventional notations which I am following. Okay, so the right hand side vector, we have 3 constraints. So this vector will have 3 elements, 100, 120 and 110. So this is my resource vector or right hand side vector, whatever you want to call it. And now I'll be inputting my coefficient matrix. Coefficient matrix will include 3 rows and 5 columns, because there are 5 variables now, so each variable is having its own column. So by looking at the given matrix, I am going to input it the values. So 1 2 1 0 0, this is the first constraint coefficient. 1 3 0 1 0, that's the second constraint. And then we have 1 1 0 0 1. This is the third constraint. So this is the matrix, the coefficient matrix, which I have just input. And now I have to define the function, like objective function, because objective functions look like the cost vector multiplied with the unknown variable vector. So I'm defining it like as a function. When we'll have the solutions, we'll be substituting those solutions into this function so that we can compute the value of the objective function. So that's the way we define the function, with the function handle at the rate. And I'm going to input a vector. In one go, I'll be inputting a vector to this function, and I know the multiplication, the function is actually C transpose X, because C I have inputted as a row vector already, and capital X I'll be capturing as my column vector, so this multiplication will be well defined. If you have inputted your C vector as a column vector, so here you need to write C transpose, because you know the vector multiplication has to make sense, but I have already inputted as a row vector, you can see, so no need to take the transpose over here. And one more thing, this B which I have just inputted, this has to be a column vector, but I have inputted as row vector. So I'll take B prime here. So that makes it column vector. So that is the complete input parameter. So this is the LPP given to us, and we can, by converting the LPP into standard form, inputting these values. And now the next thing we are going to do is a few things which we need to compute. So let me just call it initial calculations, because I just told you that how many total possible combinations of basic solutions will be existing. So that number is basically NCM. So let's first compute that what is going to be the total number of solutions. So I have just denoted it by C, capital C. So small c was the cost factor, so this is capital C, and there is a direct command in MATLAB to do this, to compute the formula NCM. So this looks like n choose k. So this is a command in MATLAB, n choose k. So it basically compute out of n variables which k variables I am choosing. So this is going to give me, so from here I have to pick up n m. So out of 5 I have to compute, I have to pick up 3 variables at a time, 3 basic variables. So basically you can say this computes NCM. So although already I have given you NCM, so this will actually compute 5C3, that how many total number of possible combinations are there. So that's capital C. And now this is going to give you just the number of combinations. Say if I'll run this in command window to show you an example, say n choose k 5 comma 3. So you look at the command window, it's 10, so 5C3. So out of 5 variables, if you want to choose 3 variables into the basis, so there will be 10 such combinations possible. So that means this command is actually giving you the number of these combinations possible, and the next command which I'm going to tell you is actually going to produce all those combinations. So that looks like, I'm denoting this by D, you can keep any name, so sorry about it, and choose k. The command goes like this, but here what I want is 1 2 n. This is a format I have to write, because I want it to be in this way. I want to create the vector out of 1 to n, it has to choose m values at a time. So this command, let me close this command is to compute all the combinations. So you can test this as well in the command window. Let me just test this one, and choose k 1 2 5 comma 3. So you can see, let me show you the output. So this is the output. So from out of the 5 numbers 1 2 3 4 5, you have to take 3 at a time. So these are all possible combinations. You can try this, there will be 10 combinations: 1 2 3 1 2 4 1 2 5, 1 3 4 1 3 5 1 4 5, 2 3 4 2 3 5 2 4 5, and 3 4 5. And there is exactly these combinations are possible. These are 10 combinations. So let me just clear this one. So that's, we have tested our commands. These commands are going to work for us. And now the next thing we have to do is choosing the basis matrix, because once we define the basic matrix, then only we'll be able to compute all the solutions. So this has to go in a iterative structure, because I'll be computing one basic feasible solution, one basic solution at a time, and I have to repeat that for all the possible combinations. So as we have just seen, we'll have 10 combinations in this example. So you have to give a for loop structure here which runs 10 times. So I'm making a general code, so it will run C time, capital C times, because capital C is the number of combinations which are possible. So for all these combinations, this will work, and the iteration index can be C. It can be whatever be the number in general. For this program, it's going to be 10. But I'm writing in general, so like writing it 1 to C. Now inside this for loop, I have to write what computation needs to be done. So as you can see, firstly, I have to figure out my basis matrix. If I am able to figure out my basis matrix, then I will be able to compute my basic solution. So to compute the basis matrix, what I need to do, firstly let me define capital X. I am initializing this with zeros n cross 1 because n is the total number of variables. So I have defined here the solution vector. So this is defined initially, the solution vector. This is initialization. We know the vector will have certain values, the variables will have certain values, but let me put all of them initially 0, and then only the basic variables will be computed, non-basic will remain by default 0. So that's the purpose of creating this 0 vector. So once you initialize this, now the next thing which I am going to do is which variables I have to put into the basis, right? So there are 10 combinations possible. Now from where I'm going to know what are those combinations? So you look at the D which we defined, this capital D which is computing from this command n choose k1 to n to m. We know this is a matrix which is having all the possible combinations. So each row of this matrix is one possible combination. I just displayed you the output. If you check that again, let me show you what was D. Sorry, we just did not calculate it the sense of D. Yeah, we calculated this. Yeah. So you can see this vector is having all the possible combinations. So every row of this is one combination. So I have to do something to extract the rows of this vector D. So first row will be the first combination, second row will be the second combination of variables. So I'm just calling it a vector. My index. Index means which variables I have to pick. So I'll be picking according to this capital D, I. There's a double colon here. This command is used basically from matrix if you want to capture its ith row, and in place of column I have written a colon here. So that means all columns values, but row is the ith row. So since I am writing it for the ith basic solution, so one by one it will take all the possible combination. When I will be equals to 1, this will be capturing the first row of the matrix D. When I will be equals to 2, this will be capturing the second row of matrix D, and so on. So this index is D, I, this, right? So you can check this command simultaneously in MATLAB command window. So let me just give it another name. Okay, so here I have not called it D, so this is answer. You can see the workspace here, answer, because I've not executed the code yet. I'm just doing the test calculations in the command window. So from here, say I want to pick up the second row, all columns. So you will see I'm getting 1, 2, 4. So this is the second row of this matrix, and all columns means all 3 entries are taken up. So that's the purpose of this command. So this index is basically going to be a vector, and this vector is having the information that which variables are going into the basis, right? So that was the purpose of using this C and D to exactly capture the basis data. Now I have decided, now I have figured which variable, like if it is 1, 2, 4, so that means first variable, second variable, and the fourth variable are going into the basis. Rest all are going to be non-basic, so they are 0. So the first variable, the first column vector of the coefficient matrix capital A, second and fourth. So that means whatever has been the data in this index, exactly that column vector I have to pick up and put that into a matrix and call it the matrix B, because the basis matrix is just coming from the coefficient matrix A. It is just I have to pick different combinations every time. So firstly I'm initializing the basis matrix. So this is comment initializing the basis matrix. So I'm initializing with an empty matrix because one by one I have to place the entries here. One by one columns have to be placed here. In one go I cannot calculate that matrix. So again I have to use a loop structure here because one by one I have to attach the columns in this basis matrix. So I'm defining another index j, and what is going to be the size of this basis matrix? M, because M is the number of equations. So M, it has to be a square matrix. So M is going to be the number of columns in the basis matrix. So these M columns now I have to define. So for j equals to 1 to M, B is defined like B, because this is how initialization works. Firstly, it will be an empty matrix, and then it will just, when it will run in iteration, it will keep on adding the columns. So which column I have to add? I have to add A from coefficient matrix. I have to add a particular column, not the row. So I have to capture, I have to extract particular row of the coefficient matrix. So that is how it is done. In the row variable, row coordinate, you have to write a column, while which column you want to extract. So in the place of column, I'll be writing that index, what index I want. So I know the vector which I've just created, named it index, that is having those indices which I want to pick. So this is index j. So jth index I'll pick. Like when j will be equal to 1, it will pick up the first entry of the index vector. Like the first entry of index vector is say 1, right? So it will put first column of the coefficient matrix here. And then it will run for j equals to 2. When j will be equals to 2, so it will be capturing the second index of this vector. So suppose that is 3. So then it will pick the third column from the coefficient matrix, right? So index is the connection between this and the matrix. That's the end. So this structure is going to give you a basis matrix. So once you have the basis matrix, now the things are easy. So this part was a bit complicated because you have to establish a combination between which vector to pick up. And if you learn this one, rest everything is going to be very easy. So once we have defined our basis matrix, so we are sure that it's going to be a square matrix. Now I want to compute the solution. So solution I'm denoting by y. I will tell you the reason why I'm denoting this with y, not with x. So we know because it's a square matrix, as I explained you on the beginning. So it has to be inverse b multiplied with right hand side vector small b, which I have already defined above. So this capital Y will be the basic solution, not complete. It will be just having the values of the basic variables. But when we want to look at the solution as a whole, so then I have to have x, right? So x is having n variables. Out of them, small m variables have been computed. They are stored in this y, and now I have to place them back into their position in the capital vector x, right? So the variables which I've just computed, I'll be placing them at their positions, and rest of the variables are already 0, non-basic, because you initialized the vector with 0. So in capital X, I have to put these values back at their places. So the places are given by again index vector, because index vector was telling me where exactly which place I picked. If I picked first, third and fourth variable, so that means this vector y contains the value of first, third and fourth variable. So in x vector, I have to place that value at the position 1, 3 and 4. I cannot just place that anywhere. So that index vector is again playing a role to decide the position there. So this is y. right? So the y vector will be directly substituted at the positions of this index vector. So this capital X is now computed. So that means we have computed the basic solution. So this is complete basic solution, right? And now I have to classify this basic solution whether this is a feasible solution or this is a non-feasible, infeasible solution. So we know the feasibility criteria is the all variables of the vector are non-negative, then it's feasible, otherwise infeasible. So that means from here onwards I'll construct two different categories, right? I'll store them separately. If this variable is, if this vector is all non-negative, I'll be storing it in another matrix and calling it the matrix of feasible solutions. So for that I need to initialize something. Let's just initialize fs. So fs is feasible solution, and ifs stands for the infeasible solution. So I'm initializing, I have initialized the feasible solution matrix because they can't be scalars, they have to be vectors. So when one by one vectors will be stored, so I'm going to get a matrix. So this is also going to be initialized infeasible solutions, although we don't need to store the infeasible solution, but let's just do that. So once you have initialized, now here I'll put a condition that if this x is greater than or equals to 0, I know I have to count this into a feasible solution. So that's how you have to store it. In the initial, you just keep on adding this. So that's it. Else, I know where it should go. It should go to IFS. So IFS X and then end. So that's how we have classified between the feasible and infeasible solutions, because at a time it will be just going into one category. And that's the end of this loop, and this is the end of this complete structure. So this whole steps, all these steps from this point to this point will be executed capital C times, means 10 times, because there are 10 possible combinations of the basis matrix. There will be 10 different basis matrix, and since we do not want to store the basis matrix at every step, so it will be just overwriting the values. The capital X will be again set to 0 every time and then do the fresh calculations. But you know, because we are storing the feasible separately and infeasible separately, so kind of every solution is being stored here into a separate matrix, and that too with its definition, whether it is feasible or it is infeasible. So now we are just left with the last part of the code. We have already figured out the feasible solutions and infeasible solutions. So the last sections of the code is we have to substituting in the objective function to exactly know which is the maximum or the minimum value. So for that I need to first define a variable S, whatever you can say, size of this feasible solution, because I need to know how many feasible solutions do I have. So feasible solution, this Fs is going to be a matrix of a particular size. Its every column is a solution. Its every column is a basic feasible solution. So I have to count how many columns this matrix has. That many basic feasible solutions will be having. The row size of this is going to be m, because n, small n, because that's the length of the vector. But the column size of this matrix is going to tell me how many basic feasible solutions I've got. So firstly I'm capturing the size of this, and then I'm saying, say, whatever you call it, say t is equal to s2. So now I'm capturing the second index of this matrix. Like if the size of this matrix is like 4 cross 5, so that means they have to pick up that 5, the number of columns. So that is coming from by capturing the second argument of this size, because the size command always gives you something like 5, 4. It's a vector which gives you the metric size. So what I'm going to do with this, I'm giving you another loop, because now each of these basic feasible solutions have to be one by one substituted into the objective function. So how many times this has to happen? This has to happen the number of times equal to the number of BFS, the basic feasible solution we have. And I just told you we have T basic feasible solution, because T is the number of columns of the FS matrix. So for this many times I have to compute. I have already computed. I have just to substitute that into the objective function. So let's just do that. So Z is the objective function value. So I have to put in f function. See, this f I initialized in the beginning. I defined it c star x. So c is already there. X it will now pick up from here. So f x. Now what should come in the place of x? So x will be picked up from the matrix fs, because in this matrix I have all columns. All columns of this matrix is each column is a basic feasible solution. So I have to pick up one column. So firstly, this FS matrix, first column will be picked up, then second column will be picked up, then third, and so on. So it has T columns, we have supposed. So you have to pick up the column like this way. We know how we do that. Kth column, because when k will be 1, it will pick up the first feasible solution vector. When k will be 2, it will be picking up the second solution, and so on. So that when we'll be substituting in the f function, it will give me some scalar value, and I want to save this every time so that I can choose the maximum or the minimum. So that's why I'm giving it an index k. So now z as a vector has been defined, and now I have to pick up the maximum value of z. That what is the maximum value of z, and what is the solution which is giving me the maximum value of z. So that means I want to capture out of these t solutions. There are t solutions, t feasible solutions in this matrix. Which one is giving me the maximum? That means at what position it is there. So for that there is a command m, say, comma r. So whatever variable name you can pick up. So let's not call it m we have already used. Say let's call it v, right? So this v equals to max. If it is a max problem, you have to use max function. If it's your min problem, you have to use a min function over here. So max z. And then you also get display your feasible solution at this. So what this command is going to do, this is going to pick up the maximum value of the objective function. It will be storing two things. First variable will store its value, and second variable will be storing its position, that out of these z values which one was the maximum, like first one, second one, or third one. So I have to exactly capture which one was the maximum. So r will be capturing its position, and so fs so that position I'll store, and out of the fs matrix that column I'll extract. So that will be my feasible solution, and that will be actually my optimal solution, right? So this is the complete code. I have already substituted everything. So let's just save this and run this. So I have saved it. So you can give any name. So say Algebraic 1. When you save it, and now we'll run it. Let's see. Hope so there is no error in this. Yeah, there is no error. It has executed, and you can see it's giving me the answer. So that's the solution. Our original problem has two variables, x1 and x2. So this is the value of x1 is 60, x2 is 20, and these are the three variables which we defined from our side, the slack variables. So s1 is 0, s2 is 0, while s3 is 30. And the maximum value of z we are getting, let's see what's that value, 5400. So all the variables are stored here. So that's the maximum value of objective function which you are getting. So that's all about this code. You can try and test it for different examples and verify your solutions. Thank you.